Let's begin. Welcome, everyone. I want to give you an overview of where we're at as we prep for our first exam, or second exam you want to call it. The first one was exam 0 because we're indexing from 0. So exam 1 was supposed to be on October 3rd, but that was from the old syllabus, so it's been moved until after fall break. So today is September 26th, so you are now in this box. And today we'll finish with most of the nonlinear solvers discussion. And I will assign homework 5 because nonlinear solvers will be on the exam. And so I at least need you to do one homework assignment before we do an exam. Okay? Next week we will have a regular lecture. We'll finish off with nonlinear solvers and we'll start on data analysis. And then next week on Thursday, we will do, so by that time, I'm hoping that you would have answered all of the feedback, provided all the feedback questions, all your questions about the material we've covered so far. So go fill out those surveys. You'll get free points on those. They count towards 2.5% of the total grade. So it's just free grades for you. Go fill up those surveys and provide me with those questions, and we will answer them together. I will answer them for you here. We'll type them in front of you, and you can ask follow-up questions. Okay? So we will have that before we go on fall break, and homework 5 will be due on that Thursday. Okay? Then no homework will be assigned on that Thursday. Then you can go off on your fall break. Okay, so you can go on your fall break. So fall break will be from, hold on, this is weird. Okay, so fall break will be from October 6th till October 13th, right, Sunday to Sunday. And then on Monday, I will have, Monday the 14th, I'll have open door office hours. Just come in if you probably be studying in the ICC lab. When I'm in my office, I'll have my door open. Just come on in and ask any questions. And then exam 1 will be on the 15th here in class. It could be, I haven't decided yet. It might be an online type exam or a handwritten type exam. It will likely be a handwritten type one. So less questions, but longer questions. And if it's handwritten, it will likely consume the entire lecture. So we will not have an opportunity to do another lecture after the exam. You'll be tired. You just want to kind of go home. Okay? So I hope this is clear. It's in the updated PDF slides. If you want to refer back to that, to this overview, it's always helpful to see where you're at. I always do these calendar overviews about 2 weeks before an exam. Let's switch back to nonlinear solvers. Today, my objectives are to get you to solve a nonlinear equation in Python, learn about fsolve and or root, which is another newer version of fsolve. We'll just talk about it briefly, and then dig under the hood to see what fsolve is doing for you. We might finish that today or not, but we will cover most of it at least, so you'll be ready to do homework 5. Okay. So last time we left off, we were asking the question, what does it mean to solve f of x equals 0? And we said that geometrically, if you plot the curve y equal f of x, and then you plot the curve y equals 0, which is a straight line at y equals 0, then f of x equals 0 is simply the intersection of two curves, f of x and 0, right? And those intersection points, there could be 1, 2, or an infinite number of intersections, right? So like sine x intersects the x-axis an infinite number of times, right? Because it keeps switching, going up and down, and oscillating forever, right? So you could have one or more roots or no roots at all. We call those red points the roots. And we say that solving an equation f of x equals 0 means finding the values of x that make f of x equal 0, obviously. Those values are often called the roots of the equation or the zeros of the equation. Now, what is critical here is to identify what root you're trying to find. You might have a formula that has many parameters, like I showed you last time. You might have volume, radius, height, length, etc. You have to identify which variable you're finding the root for, and that will define your function for which you want to find the root. So that will identify the variable of interest, okay? So bear that in mind, because we will have many formulas with parameters and one variable for which we want to find the root, okay? And then visually, we had the fun exercise last time. I asked you to point to the root. Everyone pointed their fingers at the board, and you spotted this root over here. Now, we finished with this, but I want to revisit it because we ran through it quickly. Now, this changes things a little bit. Instead of having f of x equals 0, I have the following question. Visually locate the root f of x equal 10. So now we have the curve f of x, and we want to intersect it with the curve y equal 10, which is a horizontal line at y equal 10, right? And so if you draw the line y equal 10, the intersection of the two is over there, and it's given, in this case, like 6.75. And the root of, the definition here is that the root of f of x equal alpha is the point of intersection of y equal f of x and y equal alpha. Same thing, in the previous case, alpha was 0, so it was the degenerate case. This is the more general case, okay? Now, I'm going to take this curve and put it down here. So this is f of x equal 10, okay? Same curve. Now, I'm going to take that curve and shift it by 10. So I'm going to take f of x, the same curve, and subtract from it 10, okay? And I'm going to call that r of x, a different function. R of x is f of x minus 10. And then I'll ask you, what is the root of r of x equals 0 now? Is it the same root as f of x equal 10? Remember, r of x is f of x minus 10. Visually, at least, you should be able to see that for r of x, the intersection with 0 is going to give you the same exact root. Okay? So what we did here, simply moving whatever is on the right-hand side, putting everything on the left-hand side, and renaming that function into a new function and making it equal to 0 is going to give you the same root as f of x equal 10. So the root of f of x minus 10 equals 0 is the same root as f of x equal 10. That's all I'm saying here. The root of f of x minus 10 equals 0 is the same root as f of x equal 10. Okay? Right? So the root of f of x equal alpha in general is the same as the root of r of x equal f of x minus alpha. So that's the new definition. We moved everything to the left-hand side, equals 0. Okay? Now, why did we do this? Because we want to standardize how we communicate about nonlinear solvers. When we're talking about solving an equation, a nonlinear equation, you move everything to the left-hand side, and you say, I'm finding the root or the 0 of that, of everything that was moved to the left-hand side. It's a standard way of communicating nonlinear. It's just a convention. It's a pure convention. And it actually makes it easier to write a solver that will solve for any nonlinear equation as long as it's in the form r of x equals 0. Now, why did I call it r of x? That's also a standard convention, because this is called the residual form of the equation. So whenever you have an equation, f of x could be equal to g of x even. Move everything to the left-hand side, call that r of x, and r of x equals 0 is your new system, your new function that you're working with, you're finding the root for. It will have the same root as the original equation. Okay? But that new system, that new form is called the residual form. Okay? So let's do an exercise by hand. Okay? So write log of x plus cosine x squared equals 3 in residual form. Okay, go ahead and write it in residual form. So what is the residual function, or what's the residual form for this equation? So suppose the question here would be, find the root of this equation. Well, the first step is going to be to write it in residual form. Okay? So just go ahead and write it in residual form. R of x equal what? Write that residual form, please. So just move everything to the left-hand side. Very easy. Put everything on the left-hand side and set that equal to 0. Okay. Should be straightforward. Move everything to the left-hand side and call it r of x. That's all there is. So in this case, log x plus cosine x squared minus 3 is the residual function. And when you set that equal to 0, the root, what you need to know is that the root of this equation is the same root as the equation above. Except now we're intersecting it with 0, intersecting r of x with 0. Over there, we're intersecting log and cosine with 3. But this standardizes the discussion. Okay? So this function over here is called the residual form, okay, of the original equation. Okay, so now let's go back to our original problem. We still want to solve that flood problem in the pipe. Okay, so we're headed in that direction. We want to find the height of the water after spilling 260,000 gallons, 26,000 gallons, and see if the person can go and walk in the pipe. And we're given this formula, so write this now in residual form. My standard rule of thumb, I always move everything to the left-hand side. You can move things to the right-hand side. Again, it's going to be the same thing. Math is true whether you put it on the left or on the right. My approach, I always move everything to the left-hand side, okay? Now, when you write the residual, so remember here we were looking for our variable of interest in this equation. What was it? You remember? So we were given volume, length, and radius. So we were given V, L, and R. And we're looking for H. So make sure you express your residual function R of what? Okay? What is your variable of interest? It's not X. It's not. Is it V? Is it L? You have to express your residual function also. What is the variable of interest? Okay, and name that. Let's see. Does anybody get it? No? Yes? No? Okay, I got it. Okay, so in this case, my variable of interest is H because V, L, and R are parameters. They're given to us, different conditions, different problems, but I'm always trying to find H. So my variable of interest in this nonlinear equation is H. So I explicitly say my residual function, my R is R of H. Okay, and I move everything to the left-hand side and set that equal to 0. So R of H equal to 0 has the same root as the original equation, V equal L and whatever. It's just moving things to one side of the equation. That's it. It's still the same equation. It still has the same root. Okay, so now that we have the residual form, we are ready to go to Python, because in all codes, in all Newton solver methods, in all techniques that solve nonlinear equations, they ask you, what is your residual function? If you cannot answer that question, you cannot solve your problem. You have to provide the residual function. The residual function is not the right-hand side only. Don't forget V. It's not only the left-hand side. Don't forget the right-hand side. Move everything to one side of the equation. That's your residual form. Okay, we will start learning how to drive, and then we'll dig under the hood, see how the car operates, as we've been doing so far. So we will first learn how to solve a nonlinear equation in Python. And again, one more tool to add to our arsenal and our tool belt is going to come from scipy.optimize. So NumPy is not in the business of root finding. NumPy just provides array operations and things like that. But when it comes to some serious computing, SciPy, which is scientific Python, is the sister library to NumPy and provides a lot of useful tools. One of them is under the umbrella of the scipy.optimize module. So scipy.optimize is a module for optimization. Optimization is a big class of problems in math. You find minima, maxima, roots, etc. And this umbrella, this module, provides a function, a routine called fsolve. If you've done MATLAB, if you've done some other course, they all call them fsolve. Although there's a new one in Python now called root. It looks exactly the same. The arguments are exactly the same. So you can swap fsolve with root. But fsolve is kind of just historically has been the one we've taught and learned. And it's still functional in Python. At some point, they're not going to support it probably anymore, but just like with any other function. So we will stick with fsolve for now. And the way you work with this is from scipy.optimize, you import fsolve. Okay, so now you have access directly to fsolve. Now, how does fsolve operate? It looks like this. You need a minimum of 2 arguments for fsolve. Your residual function and an initial guess. Okay? Everything else is optional. So I put those in 3 dots because they are defaulted to some value. So what we need at a minimum to use fsolve is to provide a residual function and an initial guess. So let's expand on those a little bit. Func is a Python routine that implements the residual function or the residual form of your equation. The first argument in the Python routine for the residual function must be the variable of interest or the variable for which you want to compute the root. So that's why it's important when we're writing the residual function for stuff that has a lot of parameters in it, make sure that that residual function, the first argument in there, is actually the variable of interest. So R of h or R of x or residual of L, whatever you're trying to compute. That because internally fsolve, and that's kind of the problem of teaching how to drive before explaining what's going on in the details. Inside fsolve, the residual function is being called over and over again. And when you make a call in Python, you're going to call the residual function. You're going to give it the current estimate for the root and check, is this the root or not? Right? If it's not, then continue doing something. Okay? Now, x0 is an initial guess. Now, what does this remind you of? Just last week, what we covered on Tuesday. Yes, iterative solvers. Okay? So if you remember in iterative solvers, we had to provide an initial guess and improve that initial guess. The fact that there's an initial guess here tells me, should be indicative that there's some kind of iterative procedure inside fsolve. We will learn about what that is after we finish with this. But know that you need to provide an initial guess, and it's going to try to get close to that, to the root. Okay. And the way this works is, for example, like this. I would define my residual function, a routine, and I provide it with the variable of interest. I compute something, the residual function. I return it. And then I call fsolve and tell fsolve, this is my residual. I just give it the title, the name of my residual routine, and an initial guess. Okay? All right. So now, together in class, we are going to solve this flooding problem. And this is our residual function. This is the original function, residual function. We're going to use fsolve to solve the water spill problem. Okay? Let's go ahead and do that. So grab your Python notebooks. Let's see. Okay. New notebook, Python 3. All right. Can you see the density currents from the heat coming from these projectors? Pretty interesting. Mirage effect. Okay. So for here, I'm going to import NumPy as NP, or just copy and paste from another notebook. Okay, and I'm gonna do this for my matplotlib. You don't have to have the inline thing. Some notebooks are stubborn. You have to have the inline. Mine is not, but you can keep that if you want. And then from scipy.optimize, import fsolve. Okay, so I will just call fsolve as is. All right. So now for let's check our problem here. Oops. So for fsolve, before I define v, l, and r, to use fsolve, I need to define my residual function. Okay, so let's go ahead and do that. And we say define. Let's call it pipe residual. Okay. My variable of interest is going to be h. Okay, that's the one I'm solving for. Okay, and however, I still have a bunch of parameters v, l, and r, and I'm going to assume that those are going to be provided globally. So I'm not going to pass them to the routine, residual routine. I'll teach you a way to do it later, but I'm going to assume that v, l, and r are given to us globally. They're visible everywhere in the notebook. Okay, so what that means, I can come and define them here. V is equal to 98.4 cubic meters, right? Oops. Typed every symbol in the book. Okay, so we have V equal 98.4, and L equal 15, and R equal 4. Okay, so L equal 15 meter length of pipe, and R is equal to 4 the radius of pipe. Okay. So what that means, if I define those here, V, L, and R, then anywhere I type V, L, and R, it's going to inherit those values, unless I override them somewhere. Okay? So that means for my pipe residual, as far as I'm concerned, V, L, and R are just numbers. The only unknown and variable is going to be H. So I'm going to implement this right now here. Okay? I'm going to say result equal V minus L times R squared inverse cosine R minus H over R. So I have R squared times inverse cosine. That's going to be arc cosine. Okay? There's no inv cosine. Most libraries call them arc cosine. And you can use the one from some SciPy or from NumPy. Arc cosine. Okay, now for arc cosine, I need R minus H over R. Okay, so I need another parentheses, R minus H over R. Okay. And then I have, so sorry, I keep moving back and forth as you guys are typing. Let me put this up here. Okay. Oh, it's not going to work. Okay. So V minus L into R squared minus inverse cosine R minus H over R, and then minus R minus H times square root, so MP dot square root, open parentheses, and I have 2 times R times H, I'll put 2.0, times R times H minus H squared. Okay, and then closing parentheses. You see how Python highlights the parentheses for you? So it's matching that last one with this one. You can just go, all you have to do is move the cursor next to one of the parentheses, and it will highlight the matching one, okay? So just like I'm doing here. Okay? Let's see if I zoom out a little bit. You guys can still see in the back at this level? Okay. All right, return result. So the residual routine is like any other Python routine. As far as it is concerned, it's just a routine that computes something. Okay, that's all we care about. If you remember when we did the derivative example, and I asked you to do the forward Euler for any function, we implemented the forward Euler, it took any function, and then we defined our functions as separate Python routines. That's the same thing we're doing here. This is going to be one residual function, and fsolve is we're going to call fsolve on this one. We can call it on any other one as well. Okay. And so, okay, so let's do this. Now we're done here with this one. Okay. So now, if I say fsolve, to solve this, I can say fsolve, press Shift Tab, gives you the function signature, and you can see, you can see the parameters for this function. The first one is going to be the residual, and I know this is going to be pipe residual. Okay, this is going to be pipe residual. And what about the initial guess? What is going to be our initial guess? Okay. But is that going to be close to the root? So what if there was more? What if the root was 10 times that height? Is it going to converge to that point? So you're not wrong. That's a good starting point. Okay, we can start there and see if it's gonna give us an answer or not. Soren, you had an idea? The what? Length of the pipe. Why would that be close to the root? Right, the root is the height of the water. The radius is 4 meters, so the diameter of the pipe, so if you're standing in this kind of center, the height of the pipe is going to be 8, right? The radius is 4, right? And the water is going to be, maximum level of water is going to be 8, right? Because it's going to fill the entire pipe. The smallest level is going to be 0. So how do we pick an initial guess? For iterative solvers, for linear solvers, whatever initial guess you put, you're going to converge. You'll be fine. But then in your homework, I recommended you choose an initial guess which is equal to the average temperature between the left and the right. Over here, there's no guideline. Okay, the height of the person is a good idea, but it's still like it's not robust enough for every problem. How do you pick the initial guess for every problem? The fact is, it is hard to find an initial guess, and especially, as we will learn later, this method might not converge to a root at all if you screw up the initial guess. However, there are two ways around this. The first one is, usually you are very knowledgeable of the problem, so there's an expert guess that you are selecting and choosing to find where the root is. And also in practice, that expert guess, these nonlinear equations, they are part of like bigger simulation pieces. And typically you're marching in time, so you choose the value that the initial system was at. Say you're solving for temperatures or densities or whatever. So you have an idea of how to choose the initial guess in practice. Right now we don't. Okay? But the second option would be, what if we try to visually spot where the root is? Okay? What if we this is a one-dimensional problem. We have only one unknown here, which is h. So if we plot the residual function versus h, it should give us a good idea of where the root might be located. And then we can pick a guess. So visually, you could say, okay, visually it looks like it's around 4, let's say. Well, we'll pick our initial guess there. and then pass that to fsolve, and fsolve is going to get you much better precision on that. So let's do that. Because we don't know what x0 is, I'm going to propose we plot to get an idea of the initial guess. Okay, so the initial guess should be close to the root, especially for, talk about that later. Should be close to the root, let's say that. To get an idea of what the initial guess is, one could plot the residual function in terms of the variable of interest and visually identify where the root might be located at. And then use that information as an initial guess. Okay, so now we're back to plotting. So let's create a linspace for h values, let's say, mp.linspace. And like I said, our h values are going to be either 0 or 8 meters, right? Because that's the maximum height of the pipe, right? It's 1 diameter, and the radius is 4. So I'm going to create a bunch of points from 0 to 8 because I want to plot my residual function, plt.plot. H values and then pipe residual as a function of h values. What am I doing here? Do you understand what I'm doing here? Like if you're stuck, if you don't know what plot does, you have to go understand what plot is. But you should know by now that plot and linear space is just stuff we do all the time. I'm just creating a bunch of points of h values, h equals 0, 0.1, 0.2, etc. And I want to plot the residual function to see where it crosses the x-axis so that I'm able to get an idea of where the root is. Okay? And then let's say plt.grid. So let's add a grid. Okay? And let's do that. Okay. So the residual function looks like this. It's weird. It can be negative, can be positive, doesn't matter. Don't let that scare you. It's just some arbitrary, some function, the residual function. What matters to you is if it crosses the x-axis. Because now we've standardized our discussion. We said the root is when the residual function is equal to 0. Where is that? What's your best guess for the root here? Yes. So that's the root, right? It's going to be between 2 and 3. It's going to be between 2 and 3. Right? No? Ashton?
Well, maybe a good guess right here would be 2.8.
2.8, absolutely. Could be 3, could be 2, 2.5, absolutely. But it's good news that we have a root, and we have one root. Okay? If you had multiple roots, that's going to be a problem because the routine is going to converge to the root that's closest to your initial guess. So luckily here we had only one root. And if we had picked 4, who knows if we would have converged to that. If we had picked 8 or 0, I don't know if we would have, if the code would have found this root. I always say if you have a 1D nonlinear equation, just plot it to get an idea where the root is. Now, visually, I can tell you that the water level is going to be taller than the guy. So he cannot just go down and walk because his height is 1.7 meters. This is the height of the water is going to be more than 2. So visually, I can tell you it's not going to work. But still, I want a value for h. Okay? So we can go now and call fsolve and say x0 equal 3, let's say. And then when you run that, bam, it gives you an answer. What is this value? What is it? What does it correspond to? Yeah.
In the function that you created, isn't the h times h supposed to be the square root of 2?
Oh. Here, this one?
Yeah.
Oh, yeah. That is correct. Thank you. Thank you for paying attention to that. You are right. Yep, it's right here. So they're going to change everything. Okay? Oh, there you go. Okay, so now, now our root is between 1 and 2. So I don't know if it's really going to be taller than the person or not. Right? Because I don't know if it's 1.6, 1.71, right? It's kind of hard to tell. It looks like it's around 1.5. Okay, so now let's run this again. And let's do maybe 2, x0 equal 2. All right, so it gave us a height. So what is this number? So I will ask you on the exam, the solution to a nonlinear equation with such and such and such is this number. What does that number mean? You should be able to articulate that like an essay. So an essay question. This would be a typical essay question. What is this value? That corresponds to, this is the height of the water in the pipe when 26,000 gallons have spilled into a pipe that's 15 meters long and 4 meters in diameter. Exactly that. Also, this is the root of this equation. This equation. This value is the root h of this equation given V, L, and R. Okay? I want you to capture that. This value, it means something. This is the value of h in this residual equation. This is the value that makes this equation equal to 0 exactly with the given V, L, and R. Should be a mystery. The way we did it might be a mystery to you now, but you do it a couple of times, then it becomes piece of cake. Go use fsolve to solve cosine x minus e equal e of x, e to the x, right? And find the value of x. You can do that. Piece of cake. That's an easy equation. Okay? Plot the residual, see where the root is, and use that. Use an initial guess close to the root. Okay. Now, if I change V, L, and R, so let's say we spilled 120 cubic meters and the pipe radius is 5 now, okay? Or let's say 3. So now we shrunk the pipe, we spilled more, right? So the height is going to be probably higher than the person, okay? So I change those. I can run this again. And then now I have a different residual function. So now my residual function should go from 0 to 6, right? Because that's the maximum height. Okay? Now the root is at 2, almost at 2, exactly. Okay? So if I give it 2, it's going to give me a root of 1.96. Okay? So we change that. Okay. So now let's change V, L, and R again. Let's say we spilled 80 cubic meters, 80.4 or 80 cubic meters. Pipe length is 10, and R is 4. Okay? Now my root is somewhere between, again, between 1 and 2. Okay, so we can run this again, and it's now 1.72 again. Okay, so you can use this as you vary those parameters, V, L, and R. Okay, but H is your variable of interest. V, L, and R are not variables, they're parameters. But you can change them, right? But they're not variables. The variable here is H. So now if I were to ask you in the homework, do this for 70 values of V and 70 values of L and 70 values of R, like 70 different values. You're going to have 70 times 70 times 70 ways of solving this. And it wouldn't make sense to go and manually change those or even put an array and do a for loop and change V, L, and R. Okay? A cleaner way of doing this would have been great to actually pass V, L, and R to the residual routine itself, rather than putting it as a global variable. Global variables are generally dangerous because you write them once and you forget that you defined them. You can overwrite them further down, or because you forgot that you defined them, or you think that you haven't defined them, but they were already defined, and you're using your function somewhere else, and like, what is it giving me the wrong answer? Always happens. 99% of the cases, there's an issue like that. So in general, it is not advisable to have global variables, okay? And that's actually an exam question, right? So it's not generally advisable to have global variables. Sometimes we do it when we're doing a back-of-the-envelope calculation, okay? But for serious code, when you're writing code that people are going to rely on, do not use global variables. It's foolish. It's literally foolish. Do not use global variables. Instead, pass your intent, pass those values into the function itself. Why? Because inside the routine, the scope is local. Those variables will only be defined inside that routine, not outside it, so they don't affect the outside world, they don't affect anything else. So then if you screw up somewhere else, it's going to throw an error. If you haven't defined those variables, pass it to them. Or if you've defined them elsewhere, you can actually override that and express your intent correctly. Okay? So be clear. It's always better to pass on variables to your routine. So how do we do that? fsolve allows you to do that very cleanly. Okay? And functions with arguments, so if the residual function requires one or more arguments in addition to the variable of interest, h in this case, then those can also be passed through fsolve. So what I want really here is not have to redefine these. What I want is just one loop here, go call fsolve over and over again, and give it internally different v, l, and r values. So I want to be able to pass the arguments to the pipe residual here in this fsolve. Okay? So that's what we're trying to do right now. Okay? So those can be conveniently passed via fsolve. So now if your residual looks like my residual, the first argument is always the variable of interest, the one that you're finding the root for, always, by convention. You are non-negotiable. But suppose now, in addition to that variable of interest, you have a bunch of parameters, a, b, c, d, e, f, g. In our case, going to be v, l, and r. Okay? Bunch of other parameters. So that would be your residual. Okay? Then what you could do, you can still use fsolve. It looks the same. My residual, the name of your residual routine, an initial guess, but then you add this optional argument called args, a, b, c. And then what happens here, Python internally is smart. It will understand that those will correspond to each other. That whatever you provided here, in that order, the first one is going to go to the first one, the second is going to replace the second, and the third is going to replace the third. In that exact order. Okay? Okay, so let's do this in Python. So we're going to go over again here. And now we don't want to do global variables. Instead, I'm going to define pipe residual with arguments. And always my first argument is going to be the variable in question. And then I'm going to define v, l, and r. I'm going to pass v, l, and r. It doesn't have to be in this order. Whatever order you choose, make sure you respect it when you call this function or this routine. So I'm going to copy and paste this. So now when we enter this function, this routine, this Python routine, whatever you defined for v, l, and r upstairs is going to be insignificant. Because this routine is local in scope and is going to rely to take v, whatever value is in here, l, whatever value is in here, and r, whatever value is in here. Whatever you wrote globally is going to be insignificant when you pass local variables. Although the names are the same, they're still v, l, and r, and I did that on purpose. It doesn't matter. This is just simply a slot in memory that this is related to this, and this, and this. Okay? Okay, so now we have pipe residual with arguments. Okay? Now what's cool is going to be, we're going to do fsolve, and we'll do pipe residual, okay, with pipe residual, and then x0. So first, let's say, so let's do this case, x0 equal 2. And then in this case, my arguments are going to be my v, L, and R. So my v is, let's say, 80, and then L is 15, and then R is 4. Let's go to our original case, 98.4. Okay. Okay, so now, oops, args equal, sorry, my bad. There you go. Args is equal through an error. Residual. Oh, sorry, I called the wrong one. Pipe residual with arguments. Okay, there you go. So now what's neat is that I can change the values only here. I don't have to go back and change variables globally, right? See how the root is changing as I'm changing V, L, and R? Only in this one spot. So now if I ask you solve this problem for many different values of V, different values of L, different values of R, you can just do that here in one loop. Go over all values of V, values of R, L, etc., and then just pass those over here, okay? Rather than having to pass them globally. Right? Okay, so now don't be confined to what we learned in class. Go and solve a mystery like, when does cosine x intersect with log x? Go solve that. That's a nonlinear equation. Solve it. Have the guts to do it. You're not confined to V equal L R squared or whatever I'm giving you. This is a utilitarian tool for you to use. I use this when I'm like, I was installing a radon pump at home a couple of days ago. I'm working with the guys measuring flow rates and pipe lengths, etc. I ended up with like a little, I needed to solve for a flow rate calculation. There was a nonlinear equation. Open up Python, just fsolve, and do it. I'm embellishing the story a little bit, obviously. I kind of knew the answer, but I knew I could do it with fsolve. But the guy, it's like somebody, when you show someone, look, the calculator, they're more convinced, so I had to show him the code. But it was kind of obvious to me. Anyway, so this is a tool. It's utilitarian. It's helpful. All right? Don't be confined to what I'm doing here. Go use it. See beyond what I'm showing you here. Like, go in another course, like, oh, this is a nonlinear equation. Professor Saad taught us about that. I'm going to do it with fsolve. Whatever the other course is teaching you. Okay? And then you make sure the answers are the same. And that's a great thing. Okay? It's just one more tool for you to solve, to use. All right. So let's see where we're at here. Okay. So, all right. Perfect. Let's take a couple of minutes, 3 minutes, 5 minutes, okay? 5 minutes, and we will start digging under the hood.
Using fsolve in terms of this problem giving us the total amount of water in the pipe. That's what I'm wondering.
It's not giving the total amount of water,
What
right?
is it doing? Because we get
It's
that number.
finding H. So what we're after, so remember our original, let me move it from here. So yeah, that's what I felt. It's easy to lose to lose the context,
I
right?
completely lost the context.
Yeah. So I'll remind you briefly. So if you remember, we started with a problem saying, I asked you that, okay, some fixed volume of water was spilled in a pipe of length L and radius R. So you're given V, L, and R. Those are numbers.
Yes.
And here's the formula that relates V, L, R, and H.
Yes.
And I asked you find H. And I said do it by hand, and nobody could.
And what is H?
It's the height of the water in the pipe. So this is H.
So by solving for the roots of the equation, we're getting the height of the water. Okay.
This is
And we
H, right?
compare
This is
that
the
to-
picture, right?
They give us the height of the human too, right? And
Right, uh-huh.
Okay.
Yeah, the height of the human was 1.7. The height of the water, that's how much water is going to occupy, right? Okay, yeah, sure. Hey.
I was talking to you about the exam since you changed the date. I'm not going to be here.
Okay.
So what should I do about that?
So, like, how long are you going to be out?
I land like 3 hours after.
When did you talk to me? I forgot. Did
Well,
you talk to me
no,
about
I
it?
didn't. But
Oh, you didn't?
Because it
Okay.
was supposed to be before fall break.
Yeah, there was no way we could do it before fall break because it's going to cover nonlinear solvers.
Yeah,
So,
that's fine. But I'd already.
so you'll be back on the day of the exam.
But like after, like I land at like 7 or 8 p.m.
Okay. So let me. Yeah, I'll shoot me a message
Okay.
on Canvas, and I'll find a way to work this out. Maybe.
Perfect.
Yeah.
Cool taking it before.
No. Well, I want you to at least do the homework. When are you going to leave town?
I leave Friday like midday, but I don't have school. Like I have no class.
Like the before fall break.
Yeah.
Okay, so you're out, and are you able to? I'd rather have you do the exam here, so we'll do it after you come back. Just shoot me a message. I'll think of something.
Yeah,
we'll,
like I don't have
we'll
any
work it
school
through.
on Fridays. So
Okay.
Like, if you have time on Friday, I can do anytime Friday, or I can do.
No, we'll just do it the next day after you come back.
Okay.
Yeah. But I need to find a room first. So shoot me a message, and I'll confirm that, and I'll let you know. All right, thanks. Hey, Ashton.
Hey, I'm trying to import Skippy, but it's giving me
What are you trying to import?
import Skippy.optimize, but it's giving me weird error, and I think I typed it out right.
No module named SciPy. Do you have SciPy installed?
Do I have to do I have to
Yeah, so you don't have SciPy installed. So go on Anaconda and install in your Python environment
Okay.
and install SciPy.
Gotcha.
Okay? Yeah. Test. Right. Let's resume. So your friend, your colleague asked a question that I should have reminded you of what we're doing. So going back to that pipe problem, h corresponded to the height of the water after the water has spilled into the pipe. That's why we're trying to find h. And if h is less than the height of the person, then the person can walk in the pipe. If not, if h is larger or equal, they cannot walk. Okay? So that's a visual description of what h is. It's the height of the spilled water in the pipe. That volume of water is going to occupy the pipe. It's going to settle down, right? And it's going to be a function of the length and the radius of the pipe, absolutely, obviously. Plus, and it's going to occupy up to a height h. Okay? All right. So now we are ready to start digging under the hood. fsolve is a nonlinear solver. There are a ton of nonlinear solvers, just like there are many linear solvers. If you think of the linear solvers, we had direct and iterative methods, and within direct methods, there's a bunch. Within iterative methods, we saw Jacobi, Gauss-Seidel. There's hundreds of other types of iterative solvers. Same thing for nonlinear solvers. Behind fsolve, there's one or more nonlinear solvers that are being used. In general, there are two categories of nonlinear solvers. We will learn only about one, but I want to explain both categories. The first one is called closed domain methods, closed domain nonlinear solvers. And the idea of those methods, those were the earliest methods, and they were generally quite graphical in nature. Closed domain methods, what they do, they try to estimate where the root is. So they plot the function, for example, and they try to estimate where the root is and bracket it. Choose a point on the left and a point on the right of the root. And somehow start making that bracket smaller and smaller and smaller and smaller. There's a feature of functions when they pass the x-axis, they change sign. Okay? So you can tell whether you are on the left side of a root or the right side of a root, or you're on one side of it. Okay? For the bracket. So you can always refine that bracket to stay within 2 points, one on the left, one on the right of the root, and then you keep refining that bracket until you hit the root with a given tolerance. The way we assess that we hit a root is very easy. If we have a gas, you say residual function of that gas, is it 0 or how close to 0 it is? Couldn't be easier, okay? Because it's like we are given a way to evaluate how well we are approximating that root. They are very simple, robust, they always converge. If you bracket a root on the left and the right, you are guaranteed to find it. They will always converge. However, they are not very practical because they will require you to know roughly where the root is, okay, and to estimate a bracket. But they also don't work very well for multi-dimensional problems. What if I had two linear equations with two unknowns, where both of those equations need to intersect each other and the x-axis, that's where the root is. You can't your bracket becomes like a cube, okay? And then in multi-dimensional space becomes very impractical. What if you have 1,000 equations, nonlinear equations, with 1,000 unknowns? We will learn how to solve that problem as well. But in those cases, closed domain methods do not work. So they're more kind of given for historical reasons. They're easy to think about. They help you think about iteration, and they work for one-dimensional problems very well. But we're not going to worry about that. We will not cover those this year. Now, the more robust methods, and the one that fsolve uses, are called open domain methods. And with open domain methods, instead of a bracket, you're only required to find one initial guess, either on the left or the right of the root, doesn't matter. But the method, the routine itself, should refine that guess to drive you closer to the root. Okay? So they are more efficient, less robust in the sense, they're more practical, but less robust in the sense you're not always guaranteed to find a root. And we will learn about this as we go through this lecture. So that's the problem with open domain methods, but they're more practical because you're only required one initial guess. And again, they're not guaranteed to converge, and very practical and easy to use in practice. Okay. What we will learn today is one of the open domain methods. It's the most popular one, and it's at the foundation of many nonlinear solvers, and including fsolve for sure. Okay, so I'm going to need this because I have a little video for you. Hello. Okay. I tell my 4-year-old, tell him, hello, governor. He's like, I'm not a governor. He says, like, takes it very seriously. I'm like, just messing with him. And then my other one is like, don't speak British. And so I tell him, don't speak British. And he gets so angry. So anyway, all right. Open domain methods, the one we will learn is called the Newton-Raphson method, or Newton's method. So like Euler, Newton is kind of almost everywhere. Not as much as Euler. Euler is still the best. And the idea with Newton's method is similar to iterative solvers, iterative linear solvers. We're going to start with a guess, develop a formula to improve that guess. We're going to develop a formula based on the residual function. Okay? And then we're going to keep repeating until the solution is converged. When is it converged? It's when the value of the guess makes the residual function equal 0, obviously. Okay? Just like when we talked about linear solvers, when your solution vector makes AX equal B. Okay? So I have this clip from the film 21. It's a cool film. You should watch it. It's a lot of math, some math in it. But it's also about gambling, so maybe it's not a good idea. Okay, if I can turn this off. So the mathematics of chance, okay? Let's see. Has anyone seen it? 21, have you seen it? Yeah. Okay. Do you remember the scene?
It was a while ago.
Okay, so let's see. So this is Kevin Spacey. He's a economics or math teacher. And then in the film, like he picks up these smart kids who, you know, can read cards and count cards and stuff like that. And, you know, he goes and gambles and they make money, etc. Okay. Oh, why can I cannot hear anything? My bad. Hold on. Let me see. Output. Oh. Does this work? Nope. One moment. MacBook speakers.
Now,
Okay.
all right. Now, who can explain Newton's method and how you use it?
Newton's method.
You can use it to solve nonlinear equations.
Ooh.
That's impressive. That's really good. I mean, I'm very impressed by that, especially since my class is called Nonlinear Equations. All right, now somebody tell me something I don't already know. Anyone? Bueller. Anyone? Bueller.
Newton stole it.
I'm sorry?
Newton stole it. Joseph Raphson published the same method 50 years earlier. If the start value is too far removed from true zero, then it fails.
I'm sorry. What's your name?
Ben Campbell.
Ben. So Ben Campbell suggests that Joseph Raphson was the original author of this method. Well, if that's the case, then why didn't he get any credit? Well, for one thing, Newton had a better publicist. And for another, after 1700, we know very little about Raphson.
Okay. So did you hear what he said? He said, okay, Newton stole it from Joseph Raphson, and if the guess is, what word did he use? If the guess is removed from the zero, it cannot find the zero. So let me repeat, okay?
All right. Now,
Listen.
who can explain Newton's method and how you use it?
Oops. Oh. Hold on.
All right. Really good. I mean, I'm very impressed with linear equations. All right, now somebody tell me something I don't already know.
Listen.
Anyone? Bueller. Anyone? Bueller.
Newton stole it.
Sorry?
Newton stole it. Joseph Raphson published the same method 50 years earlier. If the start value is too far removed from true zero, then it fails.
If the start value is removed from the true zero, then it fails. What it means is that if your initial guess is far away from the actual root, the method is not going to converge, which is what we've been talking about. Okay? So this is as close as kind of being accurate and faithful to the math in movies that I've seen in some time. So, okay. So we're going to learn the Newton-Raphson method. We call it Newton's method because, you know, he had a better publicist apparently. And so we have to do the math to understand the method. So every time we dig under the hood, you're going to be exposed to math because you're engineers, you're not technicians. A technician or someone who's getting just a license in doing nonlinear equations, they will learn fsolve and that's it. You as engineers, you know what's going on behind the scenes under fsolve. Keep that in mind. You need to know, you are expected to know more than just being a user of something. Okay, so given a residual function, R of x, so now we've already standardized our discussion. Any residual function, so whatever equation you're dealing with, move everything to the left-hand side, that's your residual function. So now we can talk in general about the residual functions. And lo and behold, our friend, the Taylor series, shows up again. So the idea is we're going to take the residual function and write the Taylor series about some arbitrary point x naught. Okay, we'll think about that in a minute, but we just want to see what this will do for us. Okay, so we agree that this is true. R of x around point x0 is r at x0 plus x minus x0 times r prime of x0 and so on. Okay, that's the standard Taylor series. We know this, no issues here. Okay? And this is exact. This is an equal sign. There's no approximation here. This is still exact mathematics. Now, what if we truncate this series and only take the first two terms? We're going to take those two terms. Just like we did when we computed the derivatives. We said we were looking for f prime, and we neglected everything else. We got a formula, and we used that as an approximation. We're going to do the same thing here and see what happens. Remember, I'm after solving r of x equals 0. That's what I'm after. Don't lose sight of that. I want to find x that makes r of x equal to 0. So any simplification of r of x that allows me to solve for x very quickly is going to be is my goal. Okay? So see what happens here. If we truncate and take only the first two terms, then we can approximate r of x around x0 as, it's an approximation now, r of x0 plus x minus x0 times r prime of x0. Now know that r is actually given to you, and so you also know r prime. So r prime could be a formula, a value that you can plug in here. Okay. So again, remember, we wish to solve r of x equals 0. That is, find x such that r of x equals 0. Again, I keep repeating the thing. So now, take this two-term expansion. Think about this for a minute. Treating x0 as a guess for the root of r of x equals 0, use this two-term Taylor series to improve that guess. And the hint is, set that two-term series equal to 0 and solve for x. And develop a formula that we can iterate on to get to the root. Try it. I want you to try it. These are new ideas in your mind. I cannot sugarcoat them. But if you try them, they will hit home. Okay? Take this two-term Taylor series. Suppose x0 is a root. You know r of x0, you know r prime of x0. Solve for r of x equals 0, assuming this is the approximation to r of x. And then come up with a formula. Find me that formula that I can use to iterate over and over again. Did you do it? The hint is, set r of x equals 0 in that two-term series and solve for x. We're after x. We are after x that makes r of x equal 0. So think about what I said. If we can simplify r of x so that we can solve for x to make r of x equal 0, then we can use that as a formula to keep updating s. And this two-Taylor series is a simplification of r of x, if you think about it. x0 is known. R of x0 is known because you know r. R prime of x0 is also known because you know r prime, because you know r. You can work as a group. Okay? Yes, yes. Yes, keep going, keep going. Uh-huh. You got it?
That's not right. It gives you R0.
What? Okay, so solve for x.
Yeah.
Solve for x and use that. See if you can use that to make a formula, an iterative formula. Okay? Okay. Now, can I use that to make a formula, to update? So obviously, this is going to be a crappy answer for the root. But what if I use that to improve the guess? So if I call this x1, right? This is equal to this. And then x2 is going to be equal x. Yes, you got it. Right? So r of x1, yep, r prime of x1. So, yep. And then x3 is, right?
Yes.
And then do it in general. Xk plus 1 is equal to, you got it. Okay. You should try it.
I already
That's
wasn't
right.
surprised. I had looked ahead in the slides.
Yeah. Okay. Okay, so what if you call this one x1? So obviously this is going to be a crappy answer, right? Because it's a very bad approximation. But what if you use this as a recipe? So if you call this x1, and if x0 is your guess, this is an improvement on the guess. So call it x1 is equal, so that's the improvement on x0. And then repeat, and then go to x2. x2 is going to use x1 and so on and so forth. So try that. Okay? Yep. You got it. You got it. Okay?
Oh yeah, I should generalize this.
Mm-hmm. Yes, there you go. You got it. You got it. Okay. Let me see.
That's it. The bottom.
Okay. X0. Yeah, so you can simplify. So this becomes x0 minus r over r prime, right? This is r prime and r prime, they cancel out.
But this isn't r prime over here.
This is r prime and r prime, so they cancel. So you get x0 minus r over r prime, right? So split this, split this.
Okay,
Yeah, and call this x1 and refine. Refine, okay? Okay?
So then I ended up with the
So this is, yes, this is right.
Yeah.
Well, where's your x? Yep, you have an x0 here. So you can simplify this.
yeah, and then I got the
R over R prime. Okay?
Yeah.
But that's only one improvement on the guess x0. It's going to be a very bad improvement because the approximation is really bad. So can we use it to make it keep improving the guess, reuse it and reuse it and reuse it? So think about how you would do that. So if you were to call, this is not quite right. R of x is 0, right? Yeah. Yeah, R of x is 0, okay. So now, if you started with x0, you use this to get some number. Is that number going to be the root? No, probably not, because it's a bad approximation. But it's an improvement. So what if you do this again?
And then using
So call this x1. Okay, call it x1. Now go and do x2. And do use the same formula.
it would be minus Rx.
So x2 is going to be x1, right? Minus or plus minus r, yep, minus
Rx
r of
over-
x1. There you go.
Okay.
Okay, and then no prime. No, yeah, it's the same formula, right?
And then you just
And then
plug in-
keep repeating. Okay, you got it. Okay, you got a general form. Oh, beautiful. Okay, very nice. Have you seen this before?
Well, I did see it on the slides, but
Oh,
it
okay.
makes sense.
It makes
because
sense.
That's what we did with the last one, using
Uh-huh,
k as iterations and then adding each iteration.
Okay, as long as you got that.
Yeah, that makes sense.
Yeah. Okay. Okay.
I'm getting there.
Okay, you're there. You just need to think of it. Okay, so this is an approximation to the root using an initial value of x0. So now that's an improvement on x0. Let's reuse it again. So now let's, as if we're starting from x, call this x1. So put x1, Now do x2, right? So now you're as if you're starting from x2. So this is still x1, right?
Yeah.
Okay. So what is it gonna be? Yep. That's a nonlinear tattoo.
we did it.
All right. Okay. Okay, so now generalize. Xk plus 1. Okay. Okay, so there is beauty in discovery, right? It took you, what, 5 minutes to figure this out? That's not bad. Okay, most of you did. Okay. So if I simply set r of x equals 0 in that two-term expansion, so first I know that this is an approximation to r of x. We agree to that. It's the two-term Taylor series, a huge error because we neglected a lot of terms. But we're going to say, okay, let's see where this gets us. Instead of solving the true r of x equals 0, I'm going to solve the approximation to r of x. I'm going to solve for the root in the approximation to r of x, which is that two-term. It's easy. It's an algebraic equation. It's linear. It's no longer nonlinear. It's not nonlinear again anymore. We linearize the nonlinear equation to solve for the root. So that's why we teach linear systems at the beginning. We want to turn everything into linear equations, because linear equations, you can invert them very quickly. x0 is a known value. I told you that's a guess. R of x0 is a known value. R prime of x0 is a known value, because you know what r is. So if you take that, set it equal to 0, and solve for x, it's an obvious algebraic inversion, right? So you set that equal to 0. Remember, this is an approximation to r of x. So we know that the answer, the root to this equation, is going to be a crappy value of the root. But it's a beginning of a thought. So you solve for x, you get that. How do you think about this? You say, I started with r of x0, I approximated r of x, I solved for the root of the approximation, it gave me a new value. Well, what if that new value, I use it as my new initial guess, and put it here, and solve it again, and solve it again, and again, and again. Am I going to converge? Yes, you're going to converge, if you're close to the root. Okay? So, call that x1 equal x0 plus minus r of x0 over r prime. Then x2 is going to be x1 minus r at x1 over r prime at x1, and so on. And in general, you have the generalized Newton's method. xk plus 1, this is a counter. The new guess at iteration k plus 1 is equal the old guess, which you know, minus r at the old guess over r prime at the old guess. Beautiful. Second time we do an iteration process. And why do they converge when they converge? It's because you're using the equation that you're solving. With linear systems, we solved equation 1 for x1, equation 2 for x2. We didn't solve dinosaurs. We solved the equation we're trying to solve. But we wanted to get some answer, okay? So we wanted to simplify it so we can get some answer. Okay, got 3 minutes. This is called Newton's method. Okay. Newton's method, or the Newton-Raphson method, will converge when certain conditions are met. So it's not always going to converge. But I will explain to you the geometric interpretation, and next week we can go into a little more details where we show that Newton's method sometimes does not converge if the initial guess the root can get stuck in a loop. Okay? So the interpretation of Newton's method visually is as such. Suppose you're trying to find the root of this curve. Okay, so its intersection with the x-axis. Okay? And your initial guess is this guy, x0. The first iteration, what it does, it finds r of x0 and then draws a tangent line at r of x0. And the intersection of the tangent line with the x-axis is your new guess of the root. Repeat. Draw a tangent. That's your new guess. So you see how we're converging to the root. You start with a guess. You find the intersection of that guess with the curve. You draw the tangent line, intersect it with the x-axis. That is going to be your new guess. You repeat the same process. Draw a vertical line, draw a tangent, draw a vertical line, draw a tangent, until you hit the root. And you'll converge to the root. Okay? And so on and so forth. Okay? This is why this method can be problematic, because you can get stuck in a local minimum. You'll just simply go back and forth in the minimum. You can never get out of it. That's why it's important to choose the guess close to the root. I'll show you a demo example next Tuesday on how Newton's method can get stuck in a loop. Okay? I'll see you on Tuesday. Thank you. Have a nice weekend.